Hello, it's Mr. Dobson again. This is video 7 of my video on gravitational fields. This one's on satellite motion. It's the last learning video of the series. So, we've got at this point to understand all the equations on this list. Everything from the simple concept of G right through to a version of G that works in all circumstances, Newton's law of gravitation, gravitational potentials, and then relating gravitational potential back to G. And now we're going to look at one of the consequences of gravitational fields, which is satellite motion. So we've got an idea that if we have a planet and we have something around the planet, gravity can cause that object to orbit. We're all aware of this idea. So let's have a look at what that looks like. So if we have an object here, some kind of satellite obviously in this sense meaning something that orbits a planet. A moon is a satellite of Earth, but likewise there are artificial satellites. Both can be called satellites. So let's say this object orbits in this kind of path here. It has a velocity trying to move it forwards in this direction, but it can't move forwards in that direction because there is a force pulling it towards the Earth, which is why the resultant ends up being like this, and as we change direction the resultant keeps pointing in this direction and we get a circular motion. So what is this force here? Well, it's in the title, I suppose. This is the force of gravity. So it's the force of gravity that's pulling in towards the planet that it's orbiting. But this is also very similar to when we did circular motion, or if you look at my circular motion videos. And if you look at my circular motion video, you'll see that we have a similar situation. The force, the velocity going forwards, a force towards the centre, and that made it go around the circle. Now, the force towards the centre in this case is G. The force towards the centre in the case of circular motion was called centripetal force. We have equations for both of these. So if we want to look at the equation for gravitational force, we will use this equation here, Newton's law of gravitation. Let's do it over here, so we've got it right there. So we have F is equal to minus G. I'm going to do it as the big M little m notation because we're looking about orbiting around a planet, over R squared. We also have the equation of centripetal acceleration, and then we can convert that to centripetal force, and that equation is that F is equal to minus mv squared over R. Now, if we know that the second equation is true for anything moving in a circle, there's a force towards the centre and it's governed by this, and we know that for gravitational fields this is the force towards the centre, this is gravity, these two must be the same, and therefore if these two are the same we can equate these to being the same, and we now have a new equation of minus G big M little m over R squared is equal to minus m v squared over R. Now, there's some obvious rearranging we can do here. The negatives can be cancelled out from each other. That's pretty obvious. We can then take the R from this side to that side and the M from this side to that side to give us something that relates to V squared. So if we try that, we end up with, that looks like a capital V, this is velocity, so let's draw that smaller. v squared is equal to big G, big M, little m, r over r squared, little m. Okay, some obvious cancelling here now. Get rid of the little m's, get rid of the r and the squared, and we therefore can show that the velocity of an orbiting object is equal to the square root of g m over r, which is interesting because that's this equation, which means that's actually the square root of gravitational potential. So we can find the velocity of an orbiting object, anything moving in satellite motion, by knowing three things: the mass of the planet it's orbiting, or the large object it's orbiting, the strength of gravity, and how far away it's orbiting. So this must mean there's a relationship between how fast it's going and how far it is out. We can go one step further on this as well. It's often useful to think about time periods, how long it takes to complete one orbit. So let's think about that. We can relate how long it takes to complete one orbit to velocity, because the simple idea that t, actually in this case is time period, so we'll do it as a capital T. Time period of one orbit will be the distance of the orbit divided by the speed of the orbit. So that's just a rearrangement of the simple speed equation. Now, we can work this out. For something moving round Earth, the distance, well, it's a circle. It's going to be a circumference that it moves through at the orbit r. So if we look back to our diagram here, if this object is moving at an orbit, in fact I should draw that right to the centre of the planet because it's how far from the centre, it's moving an orbit r, then it will move through a circumference of 2 pi r on every orbit. So we can actually work out the distance as 2 pi r, where r is the orbiting distance, divided by the speed. Well, we've just calculated that, so that's the square root of g m over r. Now, a little trick here, this is quite complicated. Whenever you've got an equation with this on the bottom, the square root on the bottom, that's quite tricky. We can do a little trick though. We can move this to the top if we flip the fraction inside the brackets. So we can actually say that's equal to 2 pi r square root r over g m. Now it's a little bit better, but still a bit messy. What would help now if we could take the 2 pi r in? So we do that by squaring everything and then moving it into the bracket. Again, it's a little math trick. So we can get the square root of 2 squared, which would be 4 pi squared r squared r over g m. Now, there's obviously some combination we can do there. We can combine the r's and we end up with a new equation that the time period for one rotation is the square root of 4 pi squared r cubed over g m. So this is an equation now for calculating the time period of one rotation. It's easily achievable from known equations that are on the formula sheet. Wouldn't be surprised if it's in an exam, because at this level, they're looking for you to be able to take two different formula of the formula sheet and combine them and see what you can make from them. Shows a higher level of thinking. The last point to make on this satellite motion is that if we was to consider which parts of this equation are constants, obviously the 4 is one, pi is a constant, g is a constant, and m will be constant as long as you're not changing what planet you're using, which means you've actually only got two variables here. So what's interesting for us then is to take the constants slightly out. We'll take the square root to the other side to make it slightly neater. So we'll take it back to t squared. And that's actually a square. Let's try that again. So, there we go. T squared will be equal to, so the whole constants can come out the front, 4 pi squared over gm times r cubed. Now, if we treat them constant as just one number, which it would be, then we can almost put ourselves into a situation of t squared is equal to k r cubed, which we can then simplify to say, and therefore, that t squared must be proportional to r cubed. And t squared being proportional to r cubed is actually very important because it's known as Kepler's third law. So this tells you that the orbital period for a planet is proportional to the cube of the radius from the object to the centre of that planet. This is the reason why, as you move away from the Sun, for instance, that Mercury orbits very, very quickly. The whole orbit's taking a matter of days. Then you get to Earth, which takes 365 days, and then moving further out, things like Pluto, since it was discovered, has only moved through something like 3/4 of an orbit. So as you move further and further out from Mercury, through Venus and Earth and Mars, etc., as you move further out, the orbital period gets longer and longer and longer because they're moving much, much slower, because they're orbiting a much, much greater radiuses. Theoretically, if we was to want an object to orbit at, say, a metre off the ground on Earth, it is actually possible, but the velocities that would be required would be not really feasible in an Earth's atmosphere. But it is theoretically possible, if you had no atmosphere, that an object could orbit at such a height if it was travelling fast enough. Okay, so that is a description of how we can calculate a equation for satellite motion from the equations we've already learned. And that is the last bit of the gravitational field videos. Thanks for listening.